Hello, Stat 300. This is Professor Gonzalez, and I'd like to do some problems from homework 3.3, and that is, of course, on the assignment side of things, not the adaptive. And it's going to be kind of a long one because we've got a couple different ideas here, and I kind of wanted to also lecture on it a little bit. And it's going to take a little bit of time, but you can fast forward or whatever you want to do to get to the parts you really want to see. Let's get into it. So, I'm going to go right down to some lecture notes down here. If I can get down there, let's see. Whoops, no, I don't want to cut that. Keep on going. There we go. Okay, so the first big idea here is something called z-scores. So let me kind of get into that a little bit. So here's just for instance, it kind of gives a reason for it. Who is taller, a man 73 inches tall or a woman 68 inches tall? The obvious answer is that the man is taller. However, men are taller in general than women on average. So suppose the question is asked this way: who is taller relative to their gender? A man 73 inches tall or a woman 68 inches tall, right? So like if someone said a person is 6 feet tall and or 6 foot, let's say 6'1", and they didn't tell you the gender. If it was a guy, 6'1" is, it's probably above average, but it's not crazy tall. But if it was a woman, 6'1" tall, that would be a very tall lady. So I'm sure we do kind of think in terms of relativity to someone's gender when you're talking about that. So it's kind of natural to do that. One way to answer this question is to look at your z-scores. The z-score of an individual data value tells how many standard deviations that value is from its population mean. Now that's a lot. There's a lot going on there. So I'm probably going to end up drawing some pictures pretty soon here. For example, a value 1 standard deviation above the mean has a z-score of 1, and a value 2 standard deviations below the mean has a z-score of -2. So that is super clear to me, but I've got these pictures in my head. So I think I'm going to need to make a picture. So for instance, let's see. Let's get to our formula for a z-score. How do you find a z-score? A z-score is found by taking the data point that you're talking about, and that data point could be called a raw score or a score from the population, right? But it's the actual data. In that case of heights, it would be an actual height, right? And then you subtract it from your population mean, and then you divide the whole thing by the standard deviation, and that'll make a z-score. Okay. Yeah, I think I'm going to do this at this point in time. I'm going to draw a picture for you. Let's see if that actually adds. Oh, nope, that doesn't add. Oh boy, space-wise, might not be the best place to do this. I think I'm going to zoom in a little bit. So when we're talking about these problems, we're usually talking about a bell-shaped or standard normal curve. And what that does for us is, the empirical rule can apply. And with the empirical rule, you also have the z-scores kind of follow the empirical rule in many ways. So let's say someone said the mean of a population, let's say the mean is 15, and I'm going off of an example that's coming up actually. Let's say the mean is 15. Now, I think I can do something with that, and I think I can copy that. How do I do that? Copy. Oh, that I was trying to be cool, and it didn't work. Oh, I need to paste, right? Copy it, and then paste it. There we go. I'm learning. Look at that. Okay, so what I want to do is I want to put that right below to try to highlight an idea. So let's say that here's a population and they said the mean was 15 and they said the standard deviation was, let's just say 5, I guess. So if you remember the empirical rule, they talk about, if you go one standard deviation above, you can tell one standard deviation above and below gives you a certain amount of the data. And I'm going to try that again. This is going to be a long video if I don't hurry up here. So let's say that's one standard deviation above the mean. Well, one standard deviation is 5, so that would be at 20, right? And one standard deviation below the mean would be 5 down below, right? Standard deviation is 5, so one standard deviation below would be 15 minus 5 is 10. And then another standard deviation below, and then one more to get our 3. So then we're stepping in standard deviations, right? Whoa, what the heck happened there? We're stepping in standard, I think I got seasick on that one. We're stepping in standard deviations. Maybe I get rid of that. Here we go. We're stepping in standard deviations, so we started at 15 as our mean, and we go the right by 5 more 20, and then we go another 5 more 25, and another 5 more 30. And going to the left, 15 minus 5 is 10, and then we've got 5, and then we've got 0. So we've got 5, 10, 15, 20, 25, 30. So I don't know what these numbers are, but there could be negative numbers involved. But this is scaling the population, stepping it by standard deviation. What a z-score does for us is it sort of standardizes it in the way that 0 is always going to be your mean. So 0 actually is corresponding with this 15. Okay, and a z-score of positive 1 would correspond, and let me try that again. A z-score of positive 1 is going to correspond with this 20. And a z-score of positive 2 is going to correspond with 25. And a z-score of 30 a z-score of 3 corresponds with a raw score or a score from the population or a score from your example of 30. And if you go to the left, right, a raw or population score of 10 is going to correspond with a negative 1 z-score. And a 5 corresponds with a negative 2. So in other words, what a z-score does is it takes any kind of normal distribution or a bell-shaped curve, and you've got these values from whatever the population or whatever you're studying, but by turning them into z-scores, it rescales the standard deviation. Instead of using 5s, it just uses 1. And so if another problem said the standard deviation was 3.2, then it would jump by 3.2s, and one standard deviation would be 1 z-score. So it's really kind of nice that way. It really kind of cleans things up for us in terms of simplicity. But also what that does is we sometimes when we start with a population score or a number, let's do that right now. What if it was 25? And I didn't try this yet, so this better work. But remember the formula was, it was take that raw value or that value from the population, 25, subtract it from the mean, which is 15, and then divide it by your standard deviation, 5. And so what I'm trying to show you is, a lot of times with these problems is they'll give you that number and they'll say, what's its z-score? And you can visually see it's going to be a positive 2. But this is the formula that you use. And so you've got your 25 minus 15, which gives you 10. And 10 divided by 5 gives you 2, which is clearly that same value. Okay, and you can see why 15 is going to correspond with 0 because if you use 0, right, if you use 15 as your raw score, and you crank out this z formula, 15 minus the mu, well, minus itself is going to make a 0. So who cares what the bottom is, right? Because it's 0 divided by 5, which is 0. So that 0 is always going to be corresponding to your mean in the data. All right, hopefully that helps in terms of getting a better picture of what those z-scores are. And then maybe this definition makes more sense also. But let's go to, let's answer this question. A National Center for Health Statistics study states that men height for adult men, I think I said that wrong, adult men in the U.S. Has a mean of 69.4 inches. Okay, so this is for the men. Let's use red. And we need to do that. With a standard deviation of 3.1 inches. The mean height for adult women happens to be, do I use pink? Is that being too whatever? Green, whatever. Okay, so see the mean height for adult women is, there it is right there. Oops, didn't work. There it is right there. 63.8 with a standard deviation of 2.8. So now by looking at the z-scores, it's looking at those scores relative to their own gender. And so you can see, how does this work? Well, back in the original problem, the man had a height of 73 inches and the woman had a height of 68 inches. So let's plug that into our formula. He said the man had a height of 73 inches, and then of course we take the mu, which is the mean for the men, there it is right there, minus 69.4, and then divide it by the standard deviation, which is 3.1. And so of course you're going to subtract the numerator first, then divide by 3.1, and you get a z-score for this man's height. This specific man's height of 73 corresponds to a z-score of positive 1.16. And we know, because it's positive, you know that it's to the right, it's bigger than the mean. Because remember, the mean z-score means are zeros. So you know this person is more than one standard deviation above that mean. Now the woman, is she above the mean for women? Well, let's see. So the lady in question that we're talking about has a height of 68 inches. And then we look at the mean for women, which is 63.8. She's definitely taller than the average woman. And then has a standard deviation that we divide by 2.8. And we do the math and we end up getting 1.5. So relative to their own gender, the woman that has a height of 68 is, relative to her own gender, is taller than the man that has a height of 73. And so that's one application of z-scores. The woman is taller relative to the population of women's height. Okay. Z-scores in the empirical rule. Remember how I said there's definitely a connection there? Remember the empirical rule says if you have an approximate bell-shaped curve, then if you go one standard deviation to the right, this is the mean right here, right? That's the mean. If you go one standard deviation to the right and one standard deviation to the left, this covers approximately 68% of the data. And now we can say, we can apply that to z-scores instead of just standard deviations, because remember, z-scores are just one standard deviation, whatever that standard deviation is. So now we can say one z-score to the right. Whoops, that's not the right color. So we can say one z-score to the left and one z-score to the right. And remember, once again, the mean is always 0 when we're talking about z-scores. That's going to give us approximately 68% of the data. And then we can continue on from that. Well, how about two z-scores to the left of the mean 0? Whoops, that's weird. Turned into a line. Two z-scores to the left of 0 and two z-scores to the right of 0 is going to capture about 95% of the data. And most of the data, almost all of the data, is going to be captured if we start at 0 and we go to the right. Whoops, so we go to the right 3 z-scores and to the left 3 z-scores, and that's going to capture almost all of the data, remembering there's just tiny little bits that we're not getting to out in the tails. But that's like 99.7 or 99.8, somewhere around there of the data. Okay, so there's a big idea right there, super big idea, z-scores. We'll be talking about that in this chapter, in this test, but then also it comes up a lot later on. So we're going to start wrapping our head around that idea. Quartiles. Okay, so in previous sections, we learned how to compute the mean and the median. When we're talking about quartiles, they are in the realm of the median. The median of a data set as measures, what am I saying here? And the mean and median of a data set as measures of the center. Okay, so we're looking for the center of the data. Sometimes it is useful to compute measures of position other than the center. So measures of position, so trying to get to the center of your data by using a mean or a median is great, but sometimes you want to chop the data up into quarters, into whatevers. Okay, so quartiles, just the language, quartiles refers to quarters, right? So every data, so quartiles divides the data set into 4 approximately equal pieces. And when you chop things into 4 equal pieces, you're talking about quarters, right? So it says the first quartile, denoted Q1, separates the lowest 25% of the data from the highest 75% of the data. So you don't want to be thinking about quartiles like I got a 25% on the test or something like that, because it kind of confuses the issue. A Q1 is says that you have whatever the spread of the data. When you label Q1, that's saying approximately separates the lower 25% of the data. So approximately 25% of the data is down here, and then above that would be 75% of the data. So that's what Q1 does, right? And then we keep on going. The second quartile, Q2, and by the way, Q2 is also known as the median. Makes sense. Q2 would be at the 50% mark where the median is. For 50, I should say 50 percentile, darn it. But Q2 separates the lowest 50% from the data from the highest 50% of the data. That's Q2. And Q3 has a similar idea. If we were to show the data, Q3 is going to separate the lowest 75. So down here, would be 75% of the data, and that means that above it would be approximately 25% of the data, and Q3 separates that. Okay, computing quartiles. So there's several different methods of computing quartiles. In fact, our book and Alex, the adaptive side, does slightly different things, which is super annoying, and I had to really kind of flush that out so we had consistency. And so that's why 3.3 is not going to have any adaptive questions, because 3.3, we want to have one clear way of finding quartiles and not having different ways. So the way we're picking is this way right here, which is a awesome, perfect way. I think an easy enough way. It says arrange the data from increasing order. That's what we do when we're finding the median anyways, right? We've got to increase, order it from smallest to largest. Let n be the value of the values in the data set. So let n be the number of values in the data set. So if you had 10 pieces of data, n would equal 10. To compute the second quartile, simply compute the median for the first and the third quartiles. Proceed as follows. Okay, so they're basically saying if you want to get Q2, well, we already know how to do that, because that's going to be the same thing as the median. So just do whatever we're doing with the median. What was that? Order the data from smallest to largest, count the physical middle data piece, right? And if there's specifically one data piece in the middle, circle it, that's your median. If there happens to be 2 data pieces in the middle because of if it's odd or even, right? You can have 2 data pieces in the middle. Then you just find the average of those, right? Add them up, divide by 2. Now, finding the first quartile. So think about the first quartile, like the first quarter with a dollar is 25 cents. So the way you do this is you want to multiply. So you're going to find, if you want to find the first quartile, let me get a little color here. First quartile, you take 0.25, right? So that's 25 hundredths, and multiply it by how many pieces of data you have. Okay. When you're trying to do a similar procedure, you're trying to find the third quartile. You're going to, well, the third quartile, with the third quarter in a dollar is 75 cents. So you're going to multiply 0.75 or 75 hundredths times the number of data pieces that we have. Now so that's pretty easy. Now you got to do something with the results. So this is where it gets maybe a little trickier, but not too bad. Okay, so check it out. It says if L, so when you do this multiplication, if L is a whole number, then what you have to do, now L is a position. So if you got L to be like 3, or no, let's say L was 14, it means the 14th position, the 14th piece of data. That's what L is, okay? So if L is a whole number, the quartile is the average of the number in position L and the number in position L plus 1. So basically, you take the number in that position L and then take the next one and find their average. It sounds worse than it is. I'm going to do some of these for you just so we can see it happen. Now, on the other hand, if you multiply this like 0.25 times n or 0.75 times n, and L is not a whole number, right? So it has a decimal value to the right of the point. Then you just round up to the next higher whole number, and it's not 5 and bigger goes up. It's just if there's any left over in the decimal, you just round up to the next whole number. And that next whole number is going to be the position value, the position that your quartile will be. Let's do some problems. For example, the following data presents the annual rainfall in inches in Los Angeles during the month of February over several years. Compute the quartiles for the data. So if you're going to compute the quartiles, first of all, this data has to be in order from smallest to largest, and luckily it is. And when I'm talking about the data positions, I'm going to go ahead and do those in red just so we can see. That's the first one, the second one, the third one, right? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That means 15 and 15, that one's going to be 30, and then that's going to be 45, right? So we know that we have 45 pieces of data. Okay, that's your n value. So the data already in increasing order, that's great. There are 45, so n equals 45. There's 45 pieces of data. For the first quartile, we compute the 45 pieces of data n times, since it's the first quarter, right? That's 0.25 or 25 hundredths. Now notice what we get here. We are getting 11.25. There is some decimal to the right. There's leftover decimal, not a whole number. So all you have to do is just round it up to the next whole number, which is 12. Whoops, just lost my pencil. 12. So I always say 12th, and then I say position. So people don't think it's actually 12 is the quartile. It's the 12th position. You have to go to 12. There's my 12th position right there. And that right there is going to be your Q1. And you can see Q1, the first quartile, is 0.83. And there it is right there, right? Let's do the same thing. Let's do Q2. Now Q2 is just the median, so you already know how to do that. You just find the middle, the specific middle number. So I'm gonna jump past that one since we've done that a couple times already. But Q3 is the third quarter or quartile, right? So that's 0.75, right? 75 cents is the third quarter in a dollar. And we still have the same n value of 45 data pieces. And we multiply that, we get, once again, we're still getting a value that is not a whole number. So that's not a problem. All we have to do is just round up. 33.75, round it up to 34. Now when I write 34, I usually like to say 34th position, just so we don't just get all excited and write down 34 as being the third quartile. It's the 34th position, so you got to go find it. And there's a lot of data here. That's 30. I'll go ahead and do my position numbers in red. There's 30 right there. So this is 31, 32, 33, 34. 34th position is going to be my Q3. And you can see the 34th position, what's the number there? It's 4.89, and there it is. Q3 is 4.89. So that's how you find quartiles. Visualizing the quartiles. The following is a dot plot of Los Angeles rainfall data with quartiles indicated. The quartiles divide the data set into 4 parts with approximately 25% of the data in each part. So notice when they made this dot plot, there's just a lot of dots just down here at the bottom, right? And that's they're counting. I wish they had I think this is inches of rain. They don't really say, they didn't label it. Naughty, bad people there. But I believe it's inches of rain. They're talking about inches of rain in LA. Actually, I'm not sure exactly. They said rainfall. Anyhow, the point here is, I wish they would have labeled that, but the point here is you got all these data points, and there's a whole bunch of them just kind of clustered right in here, isn't there? There's a whole bunch clustered right in here, and that's why your first quartile, I mean, it seems so small, and you think, well, it should all be evened out. But what the quartile does is it tries the best to make this 25% of the data in here, 25% of data is in here, 25% of data is in here, and 25% of the data is in there. So it just divides it into nice even quarters. Okay. All right, then moving on, percentiles. So quartiles describe the shape of a distribution by dividing it into fourths or quarters. Sometimes it's useful to divide a data set into greater number of pieces to get a more detailed description of the distribution. And when we do that, we're looking for percentiles. And percentiles, percent means per century or per 100, right? Cent or century is 100. Percentile is per 100. So instead of chopping your data into quartiles, into 4 pieces, we can be much more precise and chop them into hundredths, right? So we can pick any little hundredth that we want. Like we can say, okay, I want to see what's happening at maybe that's the 89th percentile. And if you found the 89th percentile, it would say, basically it means that 89% of your data is below. And then, so what's above? What is that, 11? 11% would be above, right? And so that's how these percentiles are working. So how do you calculate percentiles? It really may look different to you, but in my mind, and I'll see if I can convince you, it's the same formula as quartiles. Check it out. If I want to find a percentile, I take that number and divide it by 100. Well, if I was looking for the 34th percentile, well, percent means 34 out of 100. Well, you don't want to put that in your calculator, right? You want to just write it as a decimal, 34 hundredths, which is just 0.34. So really, that's the number we're going to use. So, so once again, if you want to try to find the 85th percentile, I probably should write that out. If you want to write the 85th percentile, then the value you're going to use is 0.85, right? Because 85th percentile is 85% is 85 out of 100, so it's 85 hundredths. So the rest of it is the same, though. Once again, if you find this L value, what I mean by that's the same, you're still multiplying it by the number of data values or data pieces that you have. So that's the same. Now, when you do this, you find this L value. If the L value is, and I think last time I used gold, so we're going to try to use the same color. If the L value is a whole number, then, now remember, it's a position in your data. Then you take the next position and you look at those values in those two positions, you find their average, and that's going to be that percentile. On the other hand, if you do this and the L value is not a whole number, right? It has some decimal value with it. Then you just round up to the next higher whole number, and then you look at that position, and then that is going to be your the actual number in that position is going to be your percentile. Okay, let's go ahead and do one or two here. Following presents annual rainfall in Los Angeles. Okay, so there it is again. And what are we trying to do here? It says the data is already in increasing order. That's nice for them. Thank you. There are n equals 45 values, so the same graph that we saw before. For the 60th percentile, what we do is we compute. Now, see how they're writing this in the way of 60 out of 100? But, we're just going to do this. See, if I was doing this problem, I'd write it like this. I'd say L equals 0.60, right? That's 60th, or I'm sorry, that's 60 hundredths, or just 0.6, you don't have to have the 0, and then multiply it by 45. And when we do that, you can see they got 27. So we got a whole number, so you're not just going to round it off and look at that particular position. We got to have a little bit more work. So we're going to look at, now this is 27th, we got a whole number, so we got the 27th position, we need to look at that, and we need to look at the 28th. And I'm going to write position just to remind us. Those aren't answers, those are the positions. I can't remember, how many do we have going across? I think it was 15. I guess I'm going to have to, oops, now I can't count because my pencil doesn't work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is our 15th position. That means that the next one, this must be the 30th position. So if that's 30, well, then let's just count backwards. That's 30. Then we got 39, this 38, and 37. So you want 37 and 38th position, and then we need to find the average from those. So that's where this came from, right? You see this 3.57, there it is, 3.57, plus the next one over, the next position over is 3.58. Find the average of those. Add them up, divide by 2, and that is your 60th percentile. Pay attention to what it says in rounding. Often you're rounding to 2 decimal places, but they'll specify usually on that one. This one, I think, didn't have any, it was exactly that, so he didn't have to actually round it off, but just pay attention to what it says when you're entering the data. 5-number summary. So this has to do with quartiles and medians. So the 5 numbers we're talking about, when they say 5-number summary, they're talking about taking a look at a data set. The first number is the minimum number, and you got the maximum number, right? Then you've got the median, and then you've got quartile 1 and quartile 2. Once again, this median is also known as quartile 3. So you've got quartile 1, I'm sorry, not 3. Just messed that up. The median is also known as quartile number 2. So you got quartile number 1, quartile number 2, which is the median, and quartile number 3. Okay. Outliers. An outlier is a value that is considerably larger or considerably smaller than most of the values in the data set. Some outliers results from errors. For example, a misplaced decimal point may cause a number to be much smaller or larger than the others. Some outliers are correct values and simply reflect the fact that the population contains some extreme values in it. So with outliers, as we know, outliers can really screw up our data, especially when we're talking about a mean or different things like that. So, how do you know what to throw out? So we've got we've got some guidelines to help us out with that. The first idea that we want to throw at you is the interquartile range, the IQR. How do you find the IQR? Well, the IQR is super easy to find. All you do is take your Q3 minus Q1, and that's going to be your IQR, your interquartile range. Okay, so this is called the IQR method for detecting outliers, and I see this as a real popular method, and I like it because now I just don't have to look at it and go, oh, that seems smaller than the others. I think I'm going to cross it out. That seems bigger, because some are obvious and some are not obvious. But this gives you a very, very clear-cut way to do it. So if you want to figure out your lower outlier boundary, right? So anything smaller than this, you're going to cut off your data. How do you figure it out? You take your Q1 minus 1.5 times the IQR, and that will give you the lower boundary, the lower outlier boundary. Anything smaller than that, we call it outlier. Now, on the other side of things, the upper outlier boundary, what we do is we take Q3 and well, order of operations, right? We're going to multiply 1.5 times IQR, and then we're going to add that to Q3, and that number gives us the upper outlier boundary, which means anything bigger than that is an outlier, and we can cross that out. Any data value that is less than the lower, okay, that's what it just said. Now, a box plot. A box plot is a graph that represents or that presents the 5-number summary. Along with some additional information about the data set, there are several different kinds of box plots. The one we describe here is sometimes referred as the modified box plot. So let's go ahead and highlight some of these little pieces. So what this is, and this comes from our 5-number summary, but the modified does a little bit more. So let's just start with the 5-number summary. This value right here is going to be your min, the smallest number in your data set. This value right here is going to be your max, the maximum number in your data set. I got a little caveat on that because what the heck are those then, right? So I got to make a statement about that, but the other piece is, let's continue here. Q1 is this location, the median or Q2 is that location, and Q3 is this location. So this right here, Q1 to Q3 is going to be your IQR, right? Q3 minus Q1 gives us IQR, so that's that data, right? It's the 50% in the middle, 50% of the data pieces in the middle. So that is your 5-number summary, right? Was that 5? 1, 2, 3, 4, 5. 5-number summary. The IQR threw in for extra. The modified part is using our IQR method for detecting outliers and then crossing outliers out and not including them in our min and max. So apparently what happened is they took, for the upper bound, right, they took Q3, they took that number, and then they added 1.5 times the IQR, and it turned out to be a number. So that number, that number we had placed somewhere in here, wherever that number is. Whoops, my pencil's not working again. Come on. That number is somewhere in there, and anything above that gets X'd out. Okay, we still go ahead and plot it, so we can say, hey, there was some data up here, I'll show it to you, but we're not going to use it in our statistical measures or whatever we're talking about. Box plots and shape of data set. Okay, so we've got skewed to the right. We've talked about this already. We've seen this before, skewed to the right. What does it look like with a box plot? Well, when your IQR and your median is kind of bunched to the left, that's going to have a data piece that looks symmetrical, but then it's skewed to the right because you got all this stuff that's kind of pulling it out here, right? You got data that's pulling it to the right. And then this other piece, let's see, so it says the median is closer to the first quartile. It's going to be a skew to the right. Look at this piece over here. The median is closer to the third quartile, which is causing, so the median is close to the third quartile, and it's causing all this data to kind of bunch up over here. And then we've got some data pieces out here that's kind of pulling it out this way and not making it a nice bell-shaped curve. And so in this case, we call this skew to the left. And of course, if we have a box plot, if we have a histogram that's nice and bell-shaped or normal, then our box plot, let's see, it says, then the box plot is basically symmetric as well. So you've got the endpoints and you've got the inner quartile nice and symmetrical. And you've got your median that matches up nicely. All right, okay, that is it with the notes. Now let's do the problems. And whew, man, I am starving. I should have ate something before this. The thing about this is doing this on the iPad, trying to edit it down later is such a nightmare. Sometimes it adds like 4 or 5 hours to the process. And I don't know why. It seems like it should be easier than that. But so I just try to, once I start, I don't stop. So I don't have to do any editing. But it makes for a long video. And I just, man, start to get a little tired here. You're probably tired. Wow, how many pages? 20 something, huh? Just, let's go to the beginning of this problem. There we go. Okay, first problem. Now all that stuff that we learned, let's see if we can figure this out. First of all, I think I want to put that, what was it? The formula. I'll do that in red, I guess. No, I won't. So the formula for z-scores, it is z equals that x value minus the mu divided by standard deviation. So on this first one, of course, they're telling us that a population has a mean of 15 and a standard deviation of 5. Round the answer to 2 decimal places is needed. What do we want? So part A, it says, find the z-score for a population value of 1. I'm going to use some color here. So basically, we're saying x equals 1. If x equals 1, then what is the z value? We're going to use this formula to make that happen. So we're going to put in a 1, and then we know that the mean in this problem they told us was 15, and then we have to divide by the standard deviation, which was 5, and so our z value is going to be 1 minus 15, which is negative 14 over 5, and therefore they did tell us to round. Let's see what we get. We actually get a number we don't have to round because it is exactly negative 2.8. Okay, so there's my first answer, z equals negative 2.8. The fact that the z-score is negative means it's to the left of the mean, right? So it's left of the mean, correct? And negative 2.8 is getting close to negative 3. So that is way down there. If we went to the left negative 3 and to the right positive 3 on the z-score on our z scale, that would be, remember, like 99.7% of the data. So that's a lot of the data. Looking at it, if you could imagine the picture. Find the z value or z-score when the population is 9. So in this case, we've got a population that's 9. Using my formula again, putting the values in, it's going to be 9 minus my mean, which was 15 in this problem, divided by standard deviation, which was 5. So the z-score is going to be, in this case, it's what, negative 6 over 5. So the z-score is negative 1.2. I don't have to write it again, do I? Negative 1.2. And then they throw a little curveball at us. They said, what number has a z-score of 2.8? So now they're telling us the z-score is 2.8. So you grab your formula, z equals x minus the mu over sigma, and put everything in that you know. Well, in this time we know the z, right? So we're kind of working backwards. We know the z-score, and we want to try to figure out what is the actual population number. So what number has a z-score? So what number from our data set has a z-score of 2.8? So here we go. So we're going to put in a 2.8, and that's equal to our x value. I guess I'll continue with some red for one more line of work. Minus the mean, which is still 15, divided by standard deviation, which is 5. How do you solve the problem? Well, we want to start stripping this away. We want to start isolating x. So if I multiply both sides by 5, that does a nice job at reducing. And so I multiply the right and left by 5. So if I multiply the left side by 5, 5 times 2.8 is 14. And that reduced, leaving x minus 15. I add 15 to both sides, and I get, whoops, not 1. That's a negative 15. If I add 15 to both sides, I get 29. So the answer here for part C is 29. and you'd probably just type in 29. The next problem is asking us to find the first and third quartiles rather, find the IQR and all that. So the thing that's a little bit of a pain is this one is not in order. That's the first thing that has to happen is you must put it in order from smallest to largest. Oh, it is in order. Is it in order? No, it's not. It's not in order. Dang it. Okay, so I've got to put this in order, and that's going to be really important. So let's do that up here. And I got to be accurate, so I'm going to try to be accurate. Looks like we have a 3. 1, 2, 3, 4 fours. And then 3 5s. And then 3 6s. 1, 2, 3. And then 1, 2, 3, 4, 5, 6 7s. 1, 2, 3, 4. Whoops. 1, 2, 3, 4, 5, 6 7s. A couple of 8s. A 9, and then 11. A 12, a 16, 12, 16, and 25. Probably should double check that. What's there? 1. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 24, huh? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Whew, okay, so that's good. Now, let's go ahead and do this. We need to find the first and third quartile. How do we find the first quartile? So remember, we got to find this L value, and it says we must multiply it for finding the first quartile. The first quarter is 25 cents, right? So 0.25 times the N value, which is how many data that we have here. It could be a sample number, but anyways, it's the number of data, which we just said was 24. We grab our handy dandy calculator, and actually we're just taking a quarter of 24, so we're essentially dividing 24 by 4, and so therefore L equals 6. Now remember, it says if L is a whole number, okay, now this is, I'm going to write 6th position, just so we remember. I'll use red. Whoops, there we go. That when we're calculating this, we're calculating the position. So this is 1, 2, 3, 4, 5, 6, 6th position. If it's a whole number, you got to go to the next position and take both of those numbers and find their average. Well, 5 plus 5 divided by 2 is still going to be 5, right? So the first quartile is just 5. So let me write it like this. Q1 is actually 5. Let's do this again for the third quartile. So I need to find this L value, which is just the position. I'm looking for the third quartile, so 3/4 is what, 75, so 0.75 times 24 data pieces. And when I multiply that, I end up getting, what is that, 18. 0.75 times 24 is 18. A whole number again. Now remember, this is the 18th position, and because it's a whole number, we want to look at the 18th and the next one, the 19th. So we need to do that. Let me get my color red out. I need to look at the 18th and 19th. So we've got 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So there's 18th and 19th, and the actual numbers there are 8. So you take 8 plus 8, because you want to find the average of those two numbers. Of course, that's still going to be 8. So we just found out that Q3 is 8. Now we want the IQR. That's not a problem because the IQR is just going to be Q3 minus Q2. Q3 minus Q1. That sounded funny when it came out of my mouth. Q3 minus Q1. Q3 is 8 minus Q1 is 5. So the IQR, interquartile range, is 3. Okay, keep it going, keep it going. Find the upper and lower outlier boundaries. Okay, so in order to do that, are we on the same problem here? Yeah. We want to know if there's any outliers here. So here we go. That's supposed to snap. Okay, so whoop, I lost my pen. There we go. Okay, so let's call this the lower outlier B boundary. If you could even read that. Lower outlier boundary. So how do you find the lower, let's just call this, anyways, the lower boundary. How do you find that? Well, the lower boundary is going to be Q1, whoops, let me put an equal sign there, whoops, geez, equals. It's going to be Q1 minus 1.5 times the IQR. Okay, let's see, what is that? Well, let's put in, we know all this stuff. Q1 we found is way up here is 5. Minus 1.5 times the IQR, and we found the IQR right there is 3. And we know that 1.5 times 3 is 4.5. So now we have 5 minus 4.5, and 5 minus 4.5, $5 minus 450 is just 0.5. So my lower boundary is 0.5. Let's put that up here. So that means if we have anything smaller than 0.5 on our data set, we get to cross it out as an outlier. And the smallest piece of my data is right there at 3. So there aren't any things to cross out. No outliers below that lower boundary. Let's go ahead and look at our upper outlier boundary. So to find our upper boundary, we take Q3 and add 1.5 times the IQR. So let's start filling in the blanks. Q3 was 8. 1.5 times the IQR is 3. We already found out from the last problem that right here, 1.5 times the IQR is 4.5. So now we have 8. 8 plus 4.5 gives us 12.5. 12.5 is our upper bound, upper outlier bound. So our upper outlier boundary is 12.5. That means if you see, let's go see on our data set, if there's anything bigger than 12.5, we get to call it an outlier. And there's 12, and so 12.5 would be somewhere in here. So that means that we are going to actually call that an outlier and that an outlier. And we get to cross that out of our data because it's outside the upper outlier boundary. List the outliers. Okay, it could be none, but in this case it happened to be 16 and 25. Those two guys were right there and were beyond my outlier boundary, so we get to kick it out. Let's take a look at the next problem. Are we making any headway? What number are we on here? What did we just do? Oh, man, there's no numbers. 2. 2. Okay, so now we're on 3 of 9. The good thing about this data set, it is ordered for us. Thank you. So it's kind of a big data set, but we're trying to find percentiles. So let's give you that example. Percentiles, very much like quartiles, you're going to find the position L. So you need to multiply it by, since we're trying to find the 81st percentile, 0.81, times how many data pieces do we have here? A lot. When I count this up, geez, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's 14, and then we got 28. And then 28 plus 14 is what, 42. And then this is position 56 plus another 14. So you kind of get the idea. So what's that, 60, 70, I believe. Yeah. So there's 70 pieces of data here. So that means we put a 70 right there. So now we take 0.81 times 70, and that becomes 56.7. Now remember, when your L value has a decimal, then all you do is round it up to the next whole number. The next whole number is 57. And I like to put TH 57th position, so you don't run off and say my 81st quartile is 57. It's not. You got to go to the 57th position and report what that is. So, and it's kind of nice when they're decimals because then you just round it up to the next whole number and then you don't have to find any averages. You just grab the number in the 57th position. Now this is the 56th position, so the 57th is right there. So that means our 81st quartile happens to be the number in that position, which is 59. Let's do it again, except now we're talking about the 44th percentile. So 0.44 times 70 data pieces. We multiply that, that gives us 30.8. Round it up to the next whole number, which is 31. I'm going to call it the 31st position, so we know that it's not the answer. Go look it up. 31st position. Well, that's 28. Oops, 28, 29, 30, 31. There's 31. So the actual value in the 31st position is 29. So this 44th percentile is 29. Keep it going. Let's look at the next one. They want the 18th percentile. I'm looking for the position. So I'm going to multiply this by 0.18. The number of data we have still is 70. And when I pull out my calculator and say 0.18 times 70, I get 12.6. I'm going to go ahead and, since it's a decimal, round it up to 13. I'm going to call it 13th position. So go to that 13th position and report what is at the 13th position. Well, this is 14th, so this must be 13th right here. And at the 13th position, I see the value 14. So 14 is going to be my 18th percentile. Last one on this page, I'm looking for the 65th percentile. Let's multiply it by 65 hundredths times 70 data points. And when we do the multiplication, we get another decimal, 45.5. So take that guy, round it up to 46th position, and go look it up. Oops. Where's the 46th position on my data? Well, that's 42, 42, 43, 44, 45, 46. There's my 46th position, and I see 50 in the 46th position. So 50 is my 60th percentile. That's how you do it. Standardized tests. Okay, everybody's favorite, right? SAT, ACT. So in the first one, it says, please find the z-score. So they got a bunch of information. Let's try to organize ourselves here. Let's see. Is this the one that has... Okay, so anyhow, they're giving us two different means and stuff like that. So let's get organized. It says a particular year, the mean score on an ACT test. So ACT, I'm going to use red. The mean on the ACT test is 27.5 with a standard deviation, that's a bad sigma, of 3.6. Now the other test they're talking about, that's the ACT. The other one is SAT Math, everybody's favorite, my favorite. And that is going to be, that has a mean of 514 with a standard deviation of 128. See if we could answer some questions here. Find the z-score for the ACT test that has a score of 24. Okay, remember z equals, they have a score of 24 minus, and it's the ACT, minus the mean from the ACT, whoops, which that color was red. ACT is red. So the mean from the ACT is right there, which is 27.5. divided by its standard deviation, which is 3.6. Go ahead and do the subtraction up top first, which gives us a negative 3.5 divided by 3.6. And when we put that in our calculator, we're going to get a negative 0.97 repeating 2. And it looks like we're going to put in, it doesn't say specifically how many decimal values, so let's put in 2. So the answer here is the z-score is negative 0.97. All right, next one, find the z-score for the SAT. Now, SAT was the green stuff we had going here. So SAT was green. And let's use my formula for z-scores. Z equals an SAT score of 488 minus the mean. I'm going to go ahead and use my green because mean for the SAT is 514 divided by the standard deviation, which is 128. And I'm going to let you guys calculate that, put it in the calculator. And when I put it in the calculator, I get this decimal value that keeps on going, negative 0.2031, and so on. Let's go round it to 2 decimal places. So we look at the 100th, and I got a 3 next, so it's just going to be 0.20. Of course, because that's a 0, you could just write it as 0.2. It's the same thing, right? All right, the next thing is Jose's ACT score had a z-score. So now this is where we go backwards, right? This is saying the z-score is already known. It's 1.84. The z-score is known, so we use our formula. Remember the formula, z equals that data point minus the mu divided by sigma. So in this case, we know that the z-score already is 1.84. We're going to set that equal to x is what I'm looking for. I already know the mu, so let's be careful which one. I think ACT was red. Yeah, ACT was red. So we've got to use 27.5 for a mean. And our standard deviation, here it is, 3.6. So now we've got to solve algebraically. And I know if I multiply by 3.6 over 1, why did I do that? Because it's going to reduce perfectly with that 3.6. Of course, I've got to do both sides. Multiply both sides by 3.6. And when I multiply the left side by 3.6, 3.6 times 1.84, I end up getting 6.624. That equals x minus 27.5. Now I better add 27.5 to both sides. And when I do that, I get myself an answer, which is 34.124. And that's the value. That's not a z-score. That is the actual, that's Jose's ACT score. 34.1. Let's round it to 2 decimal places, so 34.12. And then Emma's SAT score had a z-score, so the same kind of thing, had a z-score of negative 1.4. Now, when you see a negative z-score, that means it's to the left of the mean. So the person did worse than the average, or the mean. Okay, so a z-score was negative 1.4. We're talking about the SAT, which I used the color green for, so let's stay consistent. The SAT, of course, there's an x value minus what is the mu, or the mean for the SAT. It is 514. Gets divided by the standard deviation, and the standard deviation is 128. Better double check. It's already out of my head. Standard deviation is 128. There it is. Gosh, there's hair on this. Maybe I'm going bald. That stinks. Anyways, now here's our equation here. And we want to solve for x, and I really want to get rid of that division by 128. So once again, multiply by 128 on both sides, and that does a nice job of reducing. But of course, I have to multiply both sides by 128. So now I've got 128 times negative 1.4, which gives me negative 179.2. And that equals x minus 514. And I add 514 to both sides. Add, and we end up, of course, that zeroes out. I get x equals, what is that? A positive 334.8. And so that means that if Emma had a z-score of negative 1.4 in this test, her SAT test score was actually 334.8. All right, moving on. Yay! Moving on to the next problem, number 5 of 9. Blood pressure. My blood pressure is going up right now, I think. It says the 3 quartiles for systolic blood pressure in a sample of 3,165 men were shown below. Okay. So, well, they're giving us, we don't have to find the quartiles, so that's great. So if we want to find the IQR, remember the IQR is just going to be Q3 minus what? Q1. So Q3, they told us right there, Q3 is 142 minus Q1, which is 118. Therefore, the IQR is, what is that, 142 minus 118, which is 24. So find the upper and lower outliers. Okay, so remember how to do that. Just as a little note for us. No, there it goes. So a little note, lower, I'm going to call it LW, lower bound, is just going to be Q1 minus 1.5 times the IQR. So the lower bound is going to be Q1. What was Q1 again? There it is, 118 minus 1.5 times the IQR, and the IQR is right in front of us, 24. So when I multiply 1.5 times 24, I get 36. And when I take 118 minus 36, I get my lower outlier bound, which happens to be 82. So this is 82. Now what I want is my upper outlier bound, or boundary, I guess. And so Q3 plus 1.5 times the IQR is going to do it. Well, we know from the last problem, the IQR was 24. So 1.5 times 24, we know from the last problem right there is 36. So we don't really have to do that again. But our upper outlier bound, what's Q3? Q3 is right here at 142. So Q3 is 142. And we have to add that. And so our upper outlier bound is let's see, where do we go? Upper outlier bound is what? 142 plus 36 is 178. Okay, 178. And the question here, whoop, don't need that. The question here, it says a systolic blood pressure greater than 159 is considered to be high. Ooh, that's high, right? Would a blood pressure of 159 be considered an outlier? And we just found out that our lower outlier boundary and upper boundary are right here. So I mean, if I were to throw kind of a graph, make a very simple graph of what we're going to cross out, anything smaller than what is this, systolic blood pressure of 82. Anything lower than that, we're crossing out, and anything above 178, we're crossing out. And this happens to be within that range. So what's the answer? Would we cross it out? No. A blood pressure of 159 would not be an outlier. Yeah, that's it. Take a look at hazardous waste on problem number 6. Following is a list of number of cities or number of hazardous waste sites in states. In recent years, the list has been sorted into numerical order. Thank you very much. From smallest to largest, construct a box plot for these data. They also gave us the median. Okay, so let's do this in order. They gave us Q1. Q1 is 12. They gave us the median, which we could also call Q2, which is 18. You want to call that the median to remind yourself, same thing. And then they also gave us Q3, which is 32. They want us to make a box plot. So that's the 5 numbers plus outliers. There it is right there, including outliers, if any. So we're going to need to do some work here. And I don't know how much space I have. So I'm going to do IQR up here. So IQR, once again, is going to be our Q3, which is 32, minus Q1, which is 12. So IQR is 32 minus 12 is 20. So I'm doing that because I want to try to figure out my lower bound. My lower outlier bound. So this is going to be my Q1, which is 12, minus 1.5 times the IQR, which is 20. Now 1.5 times 20 is going to be 30. And so 12 minus 30 gives me a lower outlier bound of negative 18. Now when I look at my data, the smallest data point I have is 0, so there is not going to be any outliers below 0. There's nothing there, so nothing to cross out there. How about an upper outlier bound? Well, with that we take Q3, which is right in front of us, 32, plus 1.5 times the IQR, which we did over here, so I'm just going to put 30. And so our upper outlier boundary is going to be 32 plus 30 is 62. Okay, so now, are there any values above 62? And I see 58 and then 71, so 62 is right there, which is our upper bound. So that means, yeah, we definitely have some outliers that must be crossed out because they're out of our range. So that's what we have to show in our graph. This is the modified box plot because we are actually showing our outliers that we're excluding from the graph. Well, we're including it, but we're showing it as crossed out. So remember, box and whiskers, how do we do that? Well, we have to put the minimum value, and there's a minimum, 0. So we make a little, they call it whisker, kind of funny names. And then you put the maximum value. In this case, the maximum value is 58 because we crossed out the outliers, so 58. There's 60, so 58 is about there. So there's our whisker, our right-hand whisker. Now we want to make our IQR, and we just do that by graphing our Q1, which is 12. Notice they just gave us Q1, which is 12. So I go to 10, 12 is about there. I make that box a little bigger. And then I go to my median, which is 18. That's a couple back from there, so 18 is about there. These are approximates. And then Q3 is 32, so 32 is about there. And then this is my IQR that I'm going to make. That's a great sound. This is my IQR right here that I'm going to make. A little shaky there. But there is my box and whiskers. It has all the important pieces. The minimum, oops, just went to the eraser. It has the minimum, maximum. It has quarter 1, 2, and 3. And now we want to show the outliers that we crossed out. Keep on getting some calls there. Okay, so now we cross out our outliers. We have 71 that we crossed out. So let's show that right there as a cross out. Whoops. Show that as a cross out. That's approximately 71. 77, which is about there, crossed out. We have, I don't know if you can see it because I crossed it out, but we have, I think it's 91. So 91 is about there. So that's another one crossed out. I got 93, so that's about there, crossed out. And then we have 117, which is just a little 3 back from 120, and that got crossed out. So there's our modified box plot. All right. Continuing on here, another hazardous waste problem, 7 of 9. Following the list, number of hazardous waste sites, okay, but it's just a sample this time, so it's not all 50 states. These were 50 states, right, all 50. In fact, one of the states has 0 hazardous waste. That's awesome. And then one has 117, which is probably California. But now this is just a sample, so it's not all 50 states, just a sample of them. And we want to find some percentiles. Okay, so when we do this problem, we're going to, of course, have to, do we have it ordered? And yes, it is ordered. We do need to know how many pieces of data we have. I'm going to count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's, 3 rows, so that's 30. That means n equals 30, and when we're trying to find these percentiles. Okay, let's do the first one, A. So if I want to find my L value, I multiply by 0.37 to calculate 37th percentile. And then I multiply how many pieces do we have? 30. And then when I multiply 0.37 times 30, I get 11.1. Because it's a decimal, I round it to 12th. I'm going to call it 12th position. Once again, because I don't want you to write down 12 as the answer. I go to the 12th position. There's 10, 11, 12, and the actual number in the 12th position is 12. So yeah, I guess if you got that wrong, you'd luck out because the 12th position has a number 12. It doesn't always work out like that though. So now we go to the 78th percentile. L equals 78 hundredths times the number of data 30. And when we multiply that, what do we get? 0.78 times 30 is 23.4. 23.4. It's a decimal, so we round up to 24. So we got to go to the 24th position and report what that is. 24th position. So let's see, that's 10. That's going to be 20. So 20, 21, 22, 23. There it is, 24. And what's at the 24th position? I see 38. So therefore, 38 is the 78th percentile. Did we do it? We got it. Okay, next one. Following are the numbers of grams of carbohydrates in 12 ounces of espresso beverage. Ooh, coffee. Offered at a coffee shop. Construct a box plot for these data. The first quartile is, they give us quartiles, that's nice. Q1 is 25. Median is Q2, or once again, median, and that is 29. And the third quartile, Q3, is 33. Okay, unfortunately, this is not ordered from smallest to largest. Kind of stinks. So I got to order this real quick. See if I could do it. I kind of took some notes on this so I could be kind of quick on this. So we got 16, 19, 20, 23, 24, 25, another 25, 26, another 26, 27, 28, 29, another 29, 30, 30, 31, 32, 33, 33, 34, 35, 35, 46, 47. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So hopefully those are all even. So it'd be 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that looks good. Okay. So now, why the heck did I just do that? Did I need to do that? Well, I'm not looking for, I'm not looking for quartiles, right? So they already gave us a quartiles. I definitely have to do that if I was looking for quartiles. I guess we could have got away without having to do that, but we do need to check out outliers, and this kind of makes it easier for that. So that was I didn't have to do that because quartiles were given. Okay, let's construct this. What is the smallest value? Now we do have to do our lower bound, so let's take care of that. See if I can squeeze that in here. It's going to be a little bit challenging. So the lower bound, I got to change this pencil size because I'm just going to be out of space. And the lower bound, once again, is going to be 25, our Q1, minus 1.5 times the IQR. Now, what is the IQR? I guess I got to do that over here. The IQR is going to be equal to Q3, 33, minus 25. Right? 33 minus 25. And so that means the IQR happens to be 8. So back to this problem, looking for the lower outlier boundary, 1.5 times the IQR of 8. And 1.5 times 8 is 12. And 25 minus 12 gives me 13. So my lower outlier bound is 13. And when I look at my data that I took so, nicely organized, 13, 16 is within that range. So there's no outlier smaller than 16, so nothing to cross out there. What about taking a look at our upper outlier bound? Well, that's going to be Q3, which is 33 plus 1.5 times the IQR. The IQR is 8. We know that when we said 1.5 times 8, we got 12. So 33 plus 12. 33 plus 12 gives us 45. And so our upper outlier bound is 45. Now, do we have any pieces of data that are larger than 45? There is 45 would go there, and that's our upper bound. That means that we have 2 pieces of data that would be outliers and be crossed off. So this is necessary because what we're trying to do is we're trying to do our 5, or we're doing a box plot, but it's the modified box plot that runs through the outliers and crosses them out if there are any outliers by using our outlier or IQR outlier detection system, whatever. So anyways, our minimum value here you can see is 16. So I'm going to go to 16. Let's see, is this the right size now? I'm going to go to 16, which is approximately just a little more than 15. And I'm going to put a little minimum value. Maximum value after we crossed out the outliers is 35. So we go to 35 and put a little value there, upper max. There's my box and whiskers. There's my whiskers rather. Then the box part is the IQR. So my Q1 is 25. That goes right here. My median Q2 is 29, which is about right there. And my Q3 is 33, which is about there. Oh, 33, no, wait a minute. Yeah, 33 is closer. Yeah, try that again. I think Q3, well, that's probably about where I had it. Anyhow, what am I missing? I just didn't write something down. Q2, did something erase on me? I think something erased. Q2 is 29, which belongs right about here. I think I went back and undid something. You'll have to check it out. So my box looks something like this. And the whisker on the left whisker. So that's what the box plot looks like. Of course, I need to show what I crossed out. What were the outliers? Well, I had one at 46. That's about there. I had another one at 47, which is right next to it, about there. There it is, modified box plot. Here we are, 9 and 9. We're almost done. So on this one, dang it, it's not ordered. Let's see, following the numbers of carbohydrates, espressos. 12-ounce espresso beverages. I need one of those. I keep on talking about espressos. I can't leave and do it. It's kind of torturous. Let's go ahead and put these in order. So I've got them right here. 11, 12, 13, 13, 15, 18, 19, 22, 24, 24, 25, 27, I'm just going to have to wrap around, 30, 37, we got 30, 31, 34, 35, 34, 35, 34, 35, 36, 37, 36, 37, another 37, a 38, a 40, another 40, 43, 45, 48, and 50. And I hope I didn't miss anything. Does it tell us how many? No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 25. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Good. Okay, so I think I've got them all there. Now, what we need to do first is find the 27th percentile. Oh, we've done a lot of these. That's going to be, my position L value is going to be found by taking 27 hundredths times how many data pieces we just counted as 25. So now, when we multiply those two numbers, I'm getting 6.75. Because it's a decimal, I'm going to round up to 7. I'm going to call it the 7th position. I need to physically go to the 7th position. 1, 2, 3, 4, 5, 6, 7. I go to the 7th position, and 19 is the number. That means that the 27th percentile is 19. Let's do it again, except we're doing the 70th percentile. This is 0.70, or just 0.7 is the same thing. 25 data points. We multiply that, and we get 17.5. Because it's a decimal, we round it up to 18, and it's the 18th position we're interested in. So we go to the 18th position with our little red pen. 17, there's 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18th we're interested in, right? What is in the 18th position? Well, that is number 37. So 37 happens to be our 70th percentile. All right, that was a long one, and I'm going to sign off. I hope that helped out. Take care and have a good one. Bye.